In this video, we're going to discuss types of reactions. So, reactions are extremely varied, but nonetheless, there's still classes that they tend to fall into, groupings. And if you know what that class is, it's a lot easier to figure out what behaviors you're going to expect. Things like if you have gaseous reactions, you're going to need a container where everything is sealed up so the gas can't escape. If you have a solid reaction, you probably need a bowl and something to grind it. And if you have a liquid, you just need to pour them together. But you might need a fume hood in case it turns into a gas. And so types of reactions can involve what phase the material's in. Additionally, there's just kind of common reactions, things like combustion. Combustion is burning. Generally on Earth, we think about things like CH4 plus O2 going to CO2 plus water. This is a generic burning reaction, especially if it's hydrocarbons. These are our products, but you can burn lots of other stuff. You can burn iron. You make rust, Fe2O3. So the balancing of this one's a little bit fun. You end up needing 2 of that, 4 of that, and 3 of that. There we go. And so the balance reaction is a little bit larger than we're used to, but there's no reason you can't burn iron. If you've ever seen, and you go to YouTube, you can find a video, steel wool. If they fill a small container with pure oxygen gas and steel wool and throw in a match, the whole thing burns up. Combustion is just any time you're reacting a chemical, generally with dioxygen, in order to have it completely convert to the most oxidized form, which is a name for these species on the end. Now, don't confuse oxidized with oxygen. The names actually go backwards. Oxygen got its name because it causes oxidation. There is oxidation, reduction. These are more commonly known as redox, and they move electrons. So if we think of a formula, Fe2O3 plus aluminum goes to Al2O3 plus iron. Well, if we think about Fe2O3 for a minute, this is iron 3 oxide. But over here, it's just iron. There's no charge on it at all. I went from a +3 ion, and after the reaction, I was a neutral atom. My aluminum, on the other hand, starts neutral, and when it's done, this is aluminum 3 oxide. It is Al3+. We've moved electrons. There used to be electrons on the aluminum. They left and went onto the iron. And so this is a redox reaction. If you rip electrons off of one atom and move them onto another, you are doing what we call oxidation and reduction. These are actually extremely common in chemistry. Not every reaction does them, but a lot do. Moving electrons is what chemistry really is. Sometimes it's moving what you're sharing with, and sometimes it's moving them to a different atom. But these are redox reactions. Other types of reactions, things like precipitation. Makes solid. Examples here, if you've got silver nitrate, and we're going to start including subsymbols, aqueous, it just means dissolved in water. And you also have sodium chloride, dissolved in water, so AQ. Well, these will react, and you will make silver chloride solid and sodium nitrate aqueous, dissolved in water. And so those little subscripts can tell us the form, the state, the phase of the materials. These become a little more important later, but this for precipitation is rather important here because I had something that was dissolved, and then it wasn't. Literally, as you pour these together, a solid just kind of forms as a thin powder in the water and sinks to the bottom. So a precipitation reaction is anything that causes a material that was suspended and dissolved to suddenly clump together and fall out. This is why rain is a precipitation. It was a gas, and it clumped together into liquid droplets and fell out of the sky. And so really, it doesn't have to be dissolved in liquid turning solid. It can be gas turning liquid. On a rare occasion, gas turning solid. That is actually possible. If you have ammonia, NH3 gas, and hydrochloric acid gas, they will make NH4Cl, ammonium chloride, solid. So if you have two of these bottles near each other, you'll just sort of see a white misty cloud forming in between them, and then it will drift away or settle to the ground depending on how much wind there is. If you see that, you messed up. You definitely don't want to be there. But you can do it. Like I said, go look on YouTube. Some of these are definitely, you'll find videos of them if you want to see them. Well, those are specific types of observable components of reactions, but there's a lot of generic reactions. And so generically, there are combinations. A combination reaction looks like A plus B goes to C, which, hey, if we go back and look at our ammonia and hydrochloric acid right there, that is exactly what we just saw. So not only was it a precipitation, it was also a combination. So reactions can be more than one type of certain orders. I mean, there are some that are mutually exclusive, but precipitation and combination definitely work together. I brought two different things together to make a third thing. That's the idea of combination. Well, if you can combine things, you can also decompose them. So decomposition. This is basically two things together break apart. And so I had A and B combined, and they broke apart into separate components. You can actually see this example would be BH3, NH3, ammonia borane. If anybody ever goes to UW, this is an incredibly investigated molecule for trying to make hydrogen cars work. A lot of the hydrogen fuel economy of the future, if anybody remembers back during the last Bush era, there's a big push to make hydrogen cars. It doesn't really work, which is why they've not gone much of anywhere. Problem is storage. You need to store hydrogen. Pressurized hydrogen gas is explosive, so we wanted to stick it on things so it wasn't under pressure, and this was one of the molecules to do it. These, however, can break apart into borane and ammonia, neither of which you want coming out of your fuel tank. So it hasn't really been a very successful investigation. There's also things like single replacement. Examples for these is if you have A plus BC and it becomes AC plus B. Something swap its partner. So C swapped out B for A. Examples here are things like aluminum and Fe2O3. What you became was you swap those oxygens around. You became, if we balance it, Al2O3 and iron. So that thermite reaction, the rust and aluminum, that was a redox reaction, is also a single replacement reaction. It happens to be doing both. Well, if you can have a single replacement, why bother specifying it if you don't need to? So there must be double replacement. AB plus CD will become AD plus CB. And so you can swap both components. Examples for this would be things like NaCl plus AgNO3. Well, if your sodium and your nitrate are now paired, and your silver and your chloride are now paired, both things had full rearrangement. Every mole or every ion swapped with some other ion. And so this is a double replacement. These are types of reactions. There are many, many more, but a lot of them are far more specific or organic chemistry based and not inorganic chemistry based. And so just to give an idea of some of the different types of things we look for as reactions occur, and then we'll talk about more of them in detail in later sections.